All right, so we're in section 7.7 now, and this section is a little bit different because we're talking about approximating integrals instead of solving them directly, or exactly, I should say. So this section builds on something that we've already talked about all the way back in Calculus 1, actually, where you talk about left and right endpoint methods. So let's quickly just talk about what the goal of this section is. The first thing we're trying to do is evaluate specific definite integrals. And you've already talked about how to do this with the fundamental theorem of calculus, where you would find an antiderivative for a function and then evaluate that antiderivative at your upper limit and your lower limit of integration and then subtract those. And we have now covered a ton of different techniques for evaluating antiderivatives, but despite all of that, there's certain integrals that you actually cannot solve using any of the techniques that we've talked about, nor any techniques that we haven't talked about. So here's sort of a classic example. There's the integral, in this case, we're going from 0 to 1 of the function e to the x squared. This function, it turns out, does not have an antiderivative that you can express in terms of elementary functions. And elementary functions are functions that we're familiar with from algebra and calculus, things like polynomials, trigonometric functions, logarithms, exponentials, all of that kind of stuff. It can actually be shown that this function, e to the x squared, does not even have an antiderivative that we can write that way. So you really can't use the fundamental theorem of calculus on an integral like this. But integrals like this can and do show up in applications. In fact, this specific one makes appearances in probability and statistics. So if we can't evaluate this directly or exactly using the fundamental theorem of calculus, our next best bet is to try to get at least an approximation to the solution to this thing. So if you go back to calculus 1 and think about what a definite integral is in the first place, it's what we think of it as the area under a curve over some interval on the x-axis. And before we even talk about the fundamental theorem of calculus in Calc 1, we approximate these things using rectangles. So if you remember, let's say this blue curve here is the graph of f of x. And here I have an interval that I want to find the area under that curve over. X0 to x4 is what I have written here. So what we do is we take that interval, break it up into little subintervals, and then on each subinterval we build a rectangle that we're kind of using to approximate that area. And we don't need to go through this whole concept because this is not new, this is review. But I want to talk about the two methods that you talk about early on, and then we're going to kind of build on those. So here, these rectangles, I'm using the left endpoint approximation method, which means for each of these subintervals that I'm putting a rectangle on, I'm using the left endpoint to determine the height of that rectangle. And then I find the areas of those four rectangles in this case, or n rectangles more generally, and add them up. And that's where we get this. Our integral is approximately that sum of rectangles using left endpoints. In this section, we're going to use capital L with a subscript of n to represent this sum, where the n represents the total number of rectangles that we used for our approximation. So for this specific case over here, I would have called this area approximation L4 because there's 4 rectangles that I'm using. We also have right endpoint approximations where we take the subintervals and we use the right endpoint of each subinterval to determine the height of these rectangles. Then we add those up. That gives us Rn, or in this case, it would be R4 again, because we have 4 rectangles. That serves as an approximation for this definite integral. Okay, so in Calculus 1, you spend some time working with both of these. And then you eventually say that if you take the limit as n goes to infinity, that approximation becomes exact, and that's where we get the definite integral by definition. Here, we're not going to be taking any limits. We're just going to be, specifying a value of n to determine how many of these rectangles we want to add up, and we're going to use that as our approximation. But we're not really going to be using these two methods because this section is about developing better methods for getting much better approximations. So here is a better approximation method that you've actually also talked about as far back as Calculus 1. It's the midpoint rule. The midpoint rule does something similar to what our left and right endpoint approximations do. We're still building rectangles underneath this curve and then adding their areas to approximate that area under the curve. But instead of using the left or the right endpoints, we choose the midpoint of each subinterval and use that to determine the height of these rectangles. The reason this is a better method for approximating this area is because of this somewhat sort of like canceling effect that we end up with. So if you look at any one of these rectangles, this first one's a good example. You can see that part of the rectangle goes above the curve. And so this isn't exactly a triangle right here, but it looks kind of close to one. This sort of triangular-ish region is an overestimate because there's too much area accumulated up here. But then if you go to this other part of the rectangle, you can see that this leaves a void under that curve. And so there's like, this one sort of misses the mark. It's not enough area accumulated by this rectangle on this side. And so this excess and this kind of lack of area here partially cancel. Now they don't completely cancel because this area is not exactly the same as this one, but just visually we can see that they're pretty close. So this rectangle is probably a fairly good approximation for the area under the curve just over this first subinterval. And then if you look at the other rectangles, we get something kind of similar happening for each one. So the midpoint rule with that sort of semi-canceling effect is a better approximation, generally speaking, than these first two here. And here's your midpoint rule kind of written as a formula, if you want to think of it that way. So the definite integral of f of x from a to b can be approximated using the sum of those rectangles that we see over there. We're going to call that mn. M is for midpoint rule. And it's equal to delta x, which is the width of your subintervals, times the sum of fx1 bar plus fx2 bar plus, all of those, where those xi bars are just those midpoints of those subintervals. And the delta x there we can think of as b minus a over n because that's the width of each subinterval. So this is still review. Like we've still done the midpoint rule before and we're spending more time with it in this section. But we're also going to develop a couple more approximation methods for these integrals, and we're going to compare how good they are to the midpoint rule. So that's kind of why we're bringing that up again. So here's the first approximation method that's new in this section, and this is what we call the trapezoid rule. So this rule is similar to the previous three, but instead of using rectangles under the curves, we use these trapezoids. So the way that we choose these trapezoids is you still take the interval that you're integrating over, break it up into equally sized subintervals. So again, this time I'm using 4 subintervals in this picture. But instead of choosing some value inside my subinterval to determine the height of a rectangle, what we do instead is we plug both endpoints of that subinterval into our function to take us to points on the curve. So you can see here if I plug x naught into this function, it's going to take me to this value, whatever the y coordinate of that is. And then if I plug x1, it's going to take me to this value, which happens to be higher than that one. So plugging these two values in can give me two potentially different function values, but they both take me to points on the curve. And then what I do is I join those 2 points by a line segment, and that creates this trapezoid here. And I do that for all of the subintervals. Here, x1 and x2. They take me to points on my curve. I join them with a line segment. x2 and x3, plug them in, takes me to points on the curve, join them by a line segment. Same thing here with my last subinterval. Okay, so now first of all, you can see that because we're using these line segments that don't necessarily have to be horizontal the way they would in a rectangle, I can create these trapezoids that more tightly hug to the kind of curve in my graph here. So it's leaving very little empty space between the curve and each trapezoid, at least in this specific example right here. So that's one reason we like the trapezoid rule, is that it gives us shapes that are a little bit better than rectangles for conforming to the shape of that curve. In order to use this rule, though, you have to know how to find areas of trapezoids because we're going to add those up. So let's think about how that works. How do you find the area of a trapezoid? A trapezoid has an area of 1/2 times the sum of the bases, B1, B2, times the height. So that's the area of a trapezoid, and that's a trapezoid that looks like this. Okay, so I have B1 here, B2. So it has, we think of trapezoids of having a base on the bottom and a base on the top, and then the height is that guy right there. Okay, these here we can think of as trapezoids like this one, but sort of turned on its side. And it doesn't have two slanted sides the way that this one does. One of them is horizontal. So if this trapezoid is turned sideways like this, then the bases are vertical instead of being horizontal. So what does it look like to add B1 plus B2? Let's think of maybe just the area of this first trapezoid. Okay, so that first trapezoid, I'll call it A0. Or actually, let's call it A1, is the sum of the bases. I get these bases by plugging x0 and x1 into my function. 1/2 times those. So f of x0 plus f of x1 times the height of that trapezoid. Well, again, because these are like trapezoids that have been turned on their sides, the height is this horizontal length right here, but we see that that's the same thing as delta x, or the width of our subinterval, okay? Now, so this would be like the first subinterval, or sorry, the first trapezoid. If I then wanted to go and add, look at the next trapezoid, which is like A2, I can call it that. So it's like that trapezoid right there. I do the same thing, 1/2 times the sum of the bases, so that's f of x1 plus f of x2 times the height again, which is delta x. And you can see what sort of a pattern here, if I were to do this for all of these trapezoids. All of them are going to have a 1/2 and a delta x, which I can think of as delta x over 2, and I can factor that out of the sum when I want to add up all of these areas. So that's, in my trapezoid rule here, I'm seeing delta x over 2. That's like this delta x and that 1/2 factored out together. Then what you're going to be left with is a sum of a bunch of fx somethings. So notice here I have f of x0, then I have plus f of x1, and then over here, when I get to my second trapezoid, I have another f of x1. So that f of x1 is being added twice. That's why I'm seeing a 2 f of x1 here. You can see just from the picture that x2, f of x2 specifically, is going to show up in the area formula for my third trapezoid because f of x2 makes up one of the sides of that trapezoid. So since it's already showing up here and it's going to show up again in the next sum, I'm going to get a 2 times f of x2 there. In fact, you can see that same thing is going to happen for all of the shared sides of these trapezoids, because if you look at all of the sides that are kind of interior to this area, each of those is being used by 2 trapezoids. So with the exception of f of x0, this furthest left endpoint, and f of xn, this furthest right endpoint, we're doubling all of these f of x whatevers, f of xi's. But we're not going to double that left and that rightmost endpoint. Okay, so this would give me the sum of the areas of those trapezoids, and I'm going to call that Tn, because that's going to represent the total area of all of those. We use that as an approximation to that definite integral. Okay, so now let's go ahead and use both the midpoint rule and the trapezoid rule in an example. And before I jump into this one, I want to I want to mention something. So typically for these lectures, for the sections that I cover, I try to choose different examples than what your textbook shows you, just so you can use your textbook as a reference and then the lecture as like kind of more examples. I'm not doing that in this section. I'm using the exact examples that show up in the textbook, and kind of the reason I'm doing that is the integral here, this integral from 1 to 2 of 1 over x, it's a really good illustration for all of the comparison that we're going to do in this section between these approximation methods. And then on top of that, the book has a couple of really useful tables where they compare some results using this definite integral, and I wanted to use those tables. So this is kind of like the one section where I'm going to basically use all of the same material that the textbook covers. But anyways, let's go ahead and use these methods. So I'm going to approximate this definite integral from 1 to 2 of 1 over x dx. We're using the midpoint and the trapezoidal rules, and for each of these, you need to specify a value for n. Remember that n represents how many rectangles in the case of the midpoint rule, or how many trapezoids in the case of the trapezoidal rule that I'm using in my sum. Okay, so starting with the midpoint rule, M5, that's how we notate what we're finding there. The first thing I want to do is think about the interval that I'm working with. The interval here is the interval from 1 to 2, okay? And then what we're going to do is we're going to find what the width of each subinterval is. So that delta x, remember that's equal to 2 minus 1 over 5. That's the difference between my endpoints divided by whatever my n was, in this case 5. So that's going to be 1/5, or I can think of that as 0.2. Okay, so what that means is when I cut this thing up into subintervals, I'm going to have 1, 1.2, 1.2, 1.4, and so on, and I'm going to end at 1.82. There will be 5 of these in total, but the width of each one of these is 0.2. Okay, now for the midpoint rule, because I'm using the midpoint rule here first, I have to find the midpoint of each of these subintervals, and these are easy to do just by looking at them. So here, for example, x1 bar is going to equal 1.1, x2 bar is going to equal 1.3, and then for this, you know, I have kind of a dot, dot, dot there. This would be the 5th midpoint, so x5 bar is going to be 1.9. Those are the values that I want to use in this approximation. So for the midpoint rule, again, just for reference, we have it listed right here. All we're doing is we're summing f of all of those x bars and then multiplying that sum by my delta x. So our delta x in this case is 0.2, and we're multiplying that to f of 1.1 plus f of 1.3 plus f of 1.5 plus f of 1.7 plus f of 1.9. Okay, that would be equal to 0.2 times. Now f is my integrand, so it's 1 over x. So this is 1 over 1.1 plus 1 over 1.3. And we're going to go all the way down until we end at 1 over 1.9. This is where you would want to use a calculator. Don't try to do this stuff by hand. So this is going to go into a calculator. And for the sake of these approximation methods, typically you're going to want to give yourself about 6 decimal places of accuracy. So when you plug this into a calculator, you're going to get approximately 0.691908. Okay, let's do this again, but this time with the trapezoidal rule. Oop, T5. Okay, so trapezoidal rule is up here. And remember what we're doing is we're doing delta x over 2. So that's 0.2 over 2. That's 0.1. And then the sum in here uses all of the endpoints of my intervals and I'm doubling all of the interior f of x whatevers. But I'm not doing that to the exterior ones. So if I look at my subintervals here, my first endpoint is 1. I'm going to have f of 1 there, which remember that's the same thing as 1 over 1 for the function we're using. Then I'm going to have plus 2 times 1 over my next interval, or 2 over 1.2. And then 2 times 1 over my next interval, or endpoint, not interval, which is 1.4. And you can see the pattern kind of continuing here, 2 over 1.6, 2 over 1.8. And that's going to take me to my last endpoint, which is just a 2, but I don't double that last one, 1 over 2. Okay? As before, this is where you plug everything into a calculator. You get an approximation. For this guy, our decimal, when you take it to 6 decimal places, should come out to about 0.695635. Okay, so you can see that we're getting values that are relatively close to each other. They don't start to differ until we get to the thousandths place or the 3rd decimal place. But they are giving us different approximations, just very close to each other. So when you're trying to analyze like how effective an approximation method is, it's good to know a little bit about something that we call error. So when you're evaluating these approximations, we know that it's very unlikely that either of these is exactly the value of that definite integral. Because the way that they're derived, they're only approximating that area under the curve. They're not giving us exact answers unless we're really, really lucky, which really doesn't happen. So we think in terms of how far off we are from an exact answer with an approximation by considering this thing that we call an error. So the error, more specifically, is the amount that we have to add to an approximation to give us an exact value. So for example, if I'm approximating something like the integral from a to b of f of x dx, and I want to use my trapezoidal rule. My trapezoidal rule, I use Tn if I'm using n trapezoids. But this is not likely to be an exact value. It's just an approximation. So if it's just an approximation, it's off by maybe a little bit. I have to add an error term, which I'm going to call ET, T for trapezoidal rule. And this represents how far off that Tn is. Okay. If we're just trying to figure out what the error is, I could write that this way. It's equal to the true value of that definite integral minus my approximation. And we can similarly define the error for the midpoint method, EM, where this is MN over here instead of TN. Okay. Now, typically you can't know what the error is exactly. Like if you do an approximation, like the trapezoidal rule to approximate this definite integral, if we somehow were able to figure out exactly what that error term is, then we wouldn't need an approximation at all, because we could just take that known value, add it to our approximation, and boom, we have exactly the right answer. So we don't tend to know the error term exactly, but as we're going to see in a little bit, we can say something about it that's useful. So before we get to that, let's look at computing the error terms for the values that the approximations that we just did. So what's special about the approximations that we just did is we were approximating an integral that we can actually evaluate exactly, because this integrand is easy to find an antiderivative for. This one is equal to the natural log of x. We're going to evaluate that from 1 to 2, which is just equal to the natural log of 2 minus the natural log of 1. That, of course, is equal to 0. So really, it's just the natural log of 2. But for the sake of comparison, let's put that in a calculator and figure out what the natural log of 2 actually is. So the natural log of 2 is approximately 0.693147. And you can see that this is pretty close to the two approximations that we just determined. But how close depends on what those error terms are. So for example, if I want to evaluate the error for my, let's do the trapezoidal rule first. I would take the actual value of that integral, and it's, I am rounding this because I can only use 6 of those decimal places. This would go on forever, so I can't use the actual decimal representation in its entirety. But that's the actual value of my definite integral. And then I want to subtract from that the approximation that I used, or that I came up with in the previous example. So that approximation, which I have right here, is 0.69563. Okay, so when I evaluate that, I'm going to get negative 0.002488. The fact that it's negative means that my trapezoidal rule overestimated the area, so I had to add a negative error to that to get down to the exact answer. The error on my midpoint rule is found in a similar way. I take the actual value of my definite integral, which we found here, and then subtract my approximation that I used when I did the midpoint rule. That one gave me 0.691908. This time I can see that I have an underestimate for that area, so my error is going to come out positive this time. The error there was about 0.001239. Okay. Really, I should probably put approximation symbols here instead of exact or like equals, because these were rounded values. They weren't exactly what I would have gotten, but that's okay for this example to leave it that way. So I have this, make sure that negative's included in there, and I have this. Now, oftentimes when we're finding errors, we're really more interested in the absolute value of those errors than whether they're positive or negative. Even though that is useful to know, for comparison purposes, we tend to take absolute values here. So if I were to take the absolute value of my error term for the trapezoidal rule and compare it to the error for my midpoint rule, I can see that both of them are good estimates. But the error on my midpoint rule is close to half of the error of my trapezoidal rule. And what you want is a small error, because the smaller the error is, the better your approximation would have been. So what we're seeing here is an error term that's close to half of the trapezoidal rule, suggesting that the midpoint rule actually worked better in this case. The question is that typically what's going to happen? And so in the next video, we're gonna investigate that a little bit by comparing more approximations and seeing if we can find a trend.